Hello everybody, welcome back. We are going to keep on keeping on in chapter 5 here, talking about stereochemistry. Alright, the first thing I want to do is I want to get a little bit of practice here in being able to recognize stereogenic centers. If you remember from last time, I said that how do you recognize a stereogenic center? Well, you look to see if a particular atom has 4 different atoms or groups of atoms bonded to it, right? And they all have to be different from each other. All right, so let's take a look at a couple of examples. All right, start off pretty simple. Okay. Now, if you look at this one, right, on all these carbons except for one, we can see that we have at least 2 identical hydrogens, right? Going left from right, we have a CH3, a CH2, a CH2. Then you have the carbon with the Cl with it. We'll come back to that one. Then a CH2 and a CH3, right? So all of those are going to be non-stereogenic centers, right? They're not chiral centers because they have 2 identical atoms on them, right? Now the one that we skipped was this guy right over here, all right? So if we look at this, all right, we can see that we've got a Cl, all right? Not drawn, don't forget, skeletal structure. I can draw it so you can see, but we have an H there, so that's an H. Then we have 2 carbons attached right here and right here, right? They're the same type of atom, but don't forget, different atoms or different groups of atoms. Taken all together, that is an ethyl group. Taken all together, that is a propyl group, right? So that particular atom has 4 different groups. It's got a Cl, an H, an ethyl, and a propyl. So that one would be stereogenic. All right, and I'm going to redraw this because I have a bunch of crap drawn on the other one. One way that you'll frequently see stereogenic carbons or stereogenic centers or chiral centers, as they're also known, represented is a lot of times they'll be represented by an asterisk next to it. So in case you ever see this, that's generally what that means. All right, so this one has 1 stereogenic center. All right, we can look at this one. Okay, going left to right, we have a CH3, not stereogenic. Then we have a C that's got 1 H. It's got an OH. It's got a methyl group, and then it's got a 2-carbon alkene. Right, so that's definitely 4 different groups. So yeah, that one is stereogenic. Then you have the atoms and the double bond. All right, and this can be a little bit of a point of confusion for some people. All right. I'm going to just draw out the skeletal structure hydrogens here, just so you can see them. All right, it might make illustrating this a little bit easier. All right, it's pretty easy to see that this end carbon over here is not stereogenic, right? It's got 2 identical hydrogens on it. What about this guy? Well, let's see. What does this have attached to it? It's got an H. On the left, it's got a 2-carbon unit with an alcohol group. And on the right, it's got a 1-carbon, a CH2 that's double bonded to it. So all the groups that are attached to that carbon are definitely different from each other. But how many are there? There's 3, right? The double bonded CH2 still counts for only 1 group. So we don't meet that 4 different group criteria, right? The only time you can ever have stereogenic centers is when the atom is sp3 hybridized. Right, that's the only way you can have 4 different groups. So, again, this one has 1. All right. See if you guys can figure this one out. Spoiler, 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 hit the pause button. All right, let's talk about it. All right, this one also is just going to have 1 stereogenic center. It's going to have 1 right there, right? We have an NH2, we have the undrawn skeletal structure H, we have a COOH group on the right, this carboxylic acid group, and we have a fairly large carbon unit over here on the left, 4 different groups. All right. One that you might ask about, that you might be suspicious about, is that, right? Because it does have 4 groups on it. It has a couple of things sticking out. I'll draw the hydrogen. But you'll notice that, 2 of the groups, CH3 right here, those are identical. So it cannot be stereogenic. So, again, this one only has one. Now this one we can go nuts with, right? Because it's got several. All right. If you look at all these, and just for clarity, I'll draw the H's. All the ones with the methyl groups are the ones that we would probably suspect to be stereogenic. Yes. 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 And yes. Okay, so that one has 4. Very good. All right. Now, one thing that we haven't really looked at yet is looking at stereogenic centers in cyclic molecules. Cyclic molecules are just like acyclic ones in the fact they can have stereogenic centers and quite frequently do, in fact. Recognizing them is a little bit different, though, sometimes. All right, let's say we had this. Okay? So what we're going to do is we're going to look at the carbons in the ring here, and we're going to see, if they're stereogenic or not. All right. 3 of the ones in the ring I think are pretty easily identified as being not stereogenic, right? 3 of them are CH2s. The only one that we might be curious about is this guy, okay? Because we have the 2 groups on single bonds that are sticking out are H and methyl, which are definitely different. But then you have the ring, right? So how do we treat this? Here's what you do. What you do is when you look at a carbon in a ring, what you do is you sort of draw this little imaginary line, dividing it exactly in half. And then each half of the ring counts as a bonded group. Okay? So if you look at this one, we have an H, we have a methyl, and then you have each half of the ring. And if you look at the halves of the ring, what do you notice about them? In this case, they're perfectly identical. So that carbon is not stereogenic, and the molecule is not chiral. All right? However, if we tweaked it a little bit, let's just say I put a double bond right there. Okay? In that case, you see things are a lot different. We take each half of the ring. This half over here has a double bond in it, carbon-carbon double bond, whereas this one does not. All right? So this one, in fact, does have 4 different groups on that carbon in the corner. So yes, that one does have a stereogenic carbon. Okay? This takes a little bit of practice, but you get used to it eventually. All right, let's try a couple of them. All right. How about this one? We have cyclohexane, we have a couple of methyl groups, and we have a CO. All right. Now, if we look at this, again, there's a couple of carbons we might suspect. This one over here with the 2 methyl groups, that's definitely not going to be stereogenic, right? Because you have 2 CH3s that are identical. This one with the Cl is going to be the one that we're really worried about. We have a Cl, we have an H, and then we have the 2 halves of the ring. All right, it should be clear here that one half of the ring has 2 methyl groups attached to it, whereas the other one does not have any. So, yeah, this one definitely is stereogenic right there. Okay? All right, let's bump it up a notch. Okay. Let's take a look at this one. Now here we have several carbons within the ring that have stuff on them. All right. First, let's eliminate. The carbon that has the double bonded O, definitely not going to be stereogenic. Why? Because it's sp2 hybridized. By definition, it can't have 4 different groups. So that one's out. Now we're going to look at each carbon within the ring that has a methyl group on it. All right, let's start off with the one over here on the left. All right, so I'm going to go ahead and draw the H that's attached. All right, so this has a methyl group, an H. All right, so if we draw the halves of the ring, here's one half, here's the other half. All right, it should be pretty clear that these are different, right? So, because one of the halves has that double bond O, one of them doesn't. So, we can definitely say that this guy is stereogenic. Okay? So, the one on the left is stereogenic. I think if you look at the one opposite to it, this one right over here, it's basically the same thing, just in the opposite direction, right? Draw it out again on your own if you want to double check, but that one's also stereogenic. So what about the bottom one? Well, let's take a look. I want to redraw this to make it a little easier to look at. All right. What about this other one on the bottom? Well, let's see. Let's draw the H. Okay, it's got the H and the CH3. However, here, if you draw the ring in half, what do you notice about the two halves of the ring? I think you'll notice that they look pretty similar, right? In fact, they're identical. So that bottom one with the methyl group would not, in fact, be stereogenic. So when all is said and done, and you're labeling the stereogenic centers of this particular structure, you'd have one here, and you'd have one here. Just those two. Okay? All right, let's try one more. Try a pentane, a cyclopentane. If nothing else at the end of organic chemistry, hopefully you guys will be really skilled at drawing hexagons and pentagons. That's the important thing. Okay. All right, so what do you think here? Well, again, we have to look for candidates within this one. The obvious candidate is this guy, right? We have obviously two different groups hanging off the ends in the CH2NH2 group and then the CH2COOH group. Then we just have the rings. Well, if we look at this one, even though this one looks like it's got a lot going on, the two halves of the ring that are attached to that carbon, they're identical. So this one has 0 stereogenic center, so overall the molecule is not chiral. So just look closely, and you should be able to identify where the ring can be placed in, or can be sort of cut in half at the attachment to a candidate carbon, and you can figure out whether it's stereogenic or not. All right. All right, let's shift gears a little bit here. I'm going to go back to a definition, and I'm going to harken back to something I mentioned in the first video when I defined the words chiral and achiral. I made sure to say that they were adjectives, right? We can describe a molecule as being chiral, for example, as being non-superimposable on its mirror image. All right. I'm going to introduce a very, very similar term here, but this is a noun. All right. We're going to look at something called an enantiomer. All right. An enantiomer, and actually I'm going to rephrase this, not as an enantiomer, but enantiomers plural, because that's how we run into them. And we run into enantiomers in pairs. Enantiomers are defined as non-superimposable mirror image molecules of each other. All right, so, if we're describing a molecule as being chiral, that chiral molecule is likely part of a pair of enantiomers, right? So one of them's a noun, one of them's an adjective, all right? And so we've actually had a little bit of practice in drawing enantiomers, right? Drawing non-superimposable mirror images, all right? Just to give a refresher on that, you know, if we had something like this, right? And we said, okay, draw all possible stereoisomers of this molecule and identify what we call enantiomeric pairs. Just basically, you know, if you have any enantiomers. All right. Well, again, the first step is identifying chiral carbons or stereogenic carbons. We have one here. It's got a ClH, a methyl, and an ethyl. Right? And we said there were a couple of different ways to draw this. We could draw this in skeletal form like this. And you draw literally the reflection, the mirror image. By the way, I want to highlight something about this because you're going to see it pop up a lot. There's a couple of different ways to represent this one in skeletal structure. You could draw it like this. Also, you could choose to draw it like this instead. This means the exact same thing. What's happening here is we're again taking sort of that skeletal structure assumption of hydrogens, right? So, you know, when we draw the flat skeletal structures like this, you know, we left out that hydrogen just because of the skeletal structure rules. We can leave it out also on three-dimensional images, right? So this doesn't necessarily have to be put in. Sometimes you'll see it, sometimes you won't. All right. This means the same thing as this. Just wanted to let you know that. All right. This, I'll just take one of them to work with, would be a pair of enantiomers. These are two different compounds. If I wanted to draw that in skeletal form, I could draw that stereogenic carbon. All right. Again, we need two planar bonds. And we need a dash and a wedge. If I want to draw the enantiomeric pair, I can put everything arbitrary, right? For the first one, I'll just put the ethyl group up here, methyl group over here, Cl over here, and the H over there. And then all you have to do is draw the reflection, draw the mirror image. Okay. So yeah, you can convert back and forth from skeletal to condensed in any of these. Okay. Well, let's try another one. Well, actually, what I'm going to do now then is take a break because my stylus just broke. The little rubber part of it just broke, and obviously I can't draw this very well without it. So this one's going to be a shortened video. I'll get another one up as soon as possible, continuing where we left off. Bye-bye.